I don't just mean the idea of calculating Coulombs Law. I mean, what is Coulombs Law? There should be at least your qualitative idea that it is a method for calculating the force of attraction or repulsion between any two objects with charge. I would suspect that in a discussion about Coulombs Law, you have some method for discussing whether it's going to be a force of attraction or a force of repulsion, indicating also the importance of the separation distance versus the size of the charge. There should be some mention of what charge actually is, and probably an understanding of the concept of the elementary charge and the quantization of charge. All concepts we kind of talked about. It might not be a bad idea to know the difference between charging by conduction versus induction. And in just a few moments, we're going to have a bit of a conversation about that. And probably the difference between insulators and conductors. I agree, Arushi. Nice yawn. I feel the same way. So let me give you an idea of perhaps something that you should be able to think about when it comes to these kinds of questions. You should remember that it is the electron that moves around. Although we make up all these problems that indicate we can have a strong sense of positive charge and a strong sense of negative charge, in reality, the only thing we can truly manipulate are electrons. So we should always maintain the idea that there's this illusion in these problems where we can just create positive charge and have a positively charged object. The truth is, no, we stripped away electrons to make something positively charged. We are manipulating electrons whenever we manipulate charge. All right, that was our first section of discussion. We moved on away from that almost immediately to a more profound and important discussion on electric fields. There are a few qualitative ideas about electric fields I think you should remember. That electric fields point from positive charges to negative charges. They point from positive charges to negative charges. And that's not a surprise, I know, but I'm trying to make sure that I'm being thorough. So if I have 2-point charges, there will be an established electric field that will run between them. But we should realize that the negative charge ultimately has in its local vicinity this kind of spherically shaped charge around it with everything pointing inward. Similarly, in the local vicinity of our positive charge, some kind of spherically shaped charge kind of pointing away from it. But we use the concept of the test charge to kind of deal with what is the electric field at some point between them, making the argument that there's a electric field contribution in this direction from the positive charge and an electric field contribution in this direction from the negative charge, and that combines to give us a net electric field, perhaps that way, at this point. And we can do that anywhere to make the argument about what the electric field might look like around charged particles. Now, your ability to draw pictures like this is not going to be tested, but your ability to understand that the electric field is shaped by the charged particles around it will be. Mathematically, we define the electric field in terms of the force on a test charge. That is where we described it or defined it from. And we talked about the fact that it's easier for us to discuss the electric field because the electric field is something about space. Therefore, most times when we have a discussion about electric field, we'll be asking about the electric field at a specific location in space. But it shouldn't be lost on you that the unit of electric field is newtons per coulomb. Which does bring up something I had not talked about earlier that I should have, that the unit for charge is a coulomb, that the smallest amount of charge is the charge on the electron, 1.6 times 10 to the negative 19th coulombs, and that the proton has an equal but opposite amount of charge. We have formulated the electric field for a point charge directly from Coulombs Law, which would have started as QK over R squared, but the fact that it's in or should contain information about direction, I should also put in there that there is this R hat indicating that the electric field points in the direction of R away from the positive charge. But we also derived the fact that K actually represents a group of other constants, where one of them is a fundamental constant, the permittivity. Permittivity of space. So where K was 9 times 10 to the 9th, or as your textbook says, 8.99 times 10 to the 9th, that's Newton meter squared per Coulomb squared. The permittivity of free space is 8.85 times 10 to the negative 12 Coulomb squared per Newton meter squared. And none of this needs to be memorized because I will allow you to use the standard AP Physics C equation sheets, which we will talk about here in a few minutes. Questions to this point? All right. We did some problems involving point charges, both in 1 dimension and in 2 dimension. It shouldn't be too big a stretch to expect that you might be required to do a similar problem. We talked about different things like if I have 3 point charges of different values, where could I place a third charge to experience no electric field or no force from the other two? We did problems like that, but we also did problems where we took this and turned it into something like that. Maybe an equilateral triangle that, made for, fun geometry, I guess. And I use that word fun really sparingly here. But, it could be something like this, where I ask what is the direction and magnitude of the electric field on this charged particle here, giving you that this is R and this length is 1.5 R and this is R. So maybe something like that. No fun and tedious, sure, but not terrible. Not terrible. At least I don't think it's terrible. Tedious, though. I would hate it if this were on the test if it were me, but this is our content. Questions yet? All right. Which brings us to Gauss. Which bothers me that it's Gauss's law like that with 3 S's in a row. I always thought that when you had to make the possessive of a word ending in S, you just left the apostrophe there. But I even looked it up. In the textbook, they put the apostrophe S and say Gauss's law instead of Gauss law. Yeah. Is that what it is? Yeah. Okay. I guess there's only one Gauss. He was amazing. I guess. I don't know. I don't know anything about it. As a scientist goes, I know nothing about him. Now, Gauss's law has 2 parts to it, the Q enclosed and the flux. They're equal. The test will try and trick you by asking you questions about flux but giving you information about charge. or giving you information about flux and asking about charge. Either way, it's in your best interest to realize that this is the law itself. You don't necessarily have to calculate the flux. If they ask for flux, they might be giving you hints about using how much charge is available. Multiple choice questions tend to play with the idea of having positive charges and negative charges in a space with multiple possible Gaussian surfaces, asking you questions about which Gaussian surface has zero flux, with an attempt to try and see if they can catch you looking. So expect there to be multiple choice questions that play around with this idea. But also, you should expect that I'm going to ask you to use Gauss's law in a manner consistent with what we've talked about, which is likely to include your ability to use the integral calculation of flux, being able to recognize the 3 parts of calculating flux, or really the 4 parts of calculating flux. In that, I expect you to be able to deal with the fact that the electric field has direction, the area has direction. You have to sum over a closed surface and take the 2 directions into account. So, any of the 3 major shapes are fair game. And of those shapes, remember, point charge produces what we expect for the electric field. A infinite line of charge, you should remember that it's going to be similar, but and it is away from the line. And of course, a sheet of charge having a constant electric field. The 3 basic shapes, I'd have that information. It's not hard to prove, but it's always nice to have it available. What will not be on the test tomorrow? I will not ask you to deal with a uniform charge distribution where you have to use Coulombs Law. I introduced it because it needed to be introduced at that moment, but until your mathematics skills have improved and you've learned a little bit more about the integral, it's just not an appropriate problem to ask. So a charged bar or a charged disk or a finite charged rod, those will not be asked tomorrow. I will not be asking you to make some kind of reach with this. We'll save this until get a little more calculus. So although introduced and we gave it a couple 3 days, not going to be on the test tomorrow. All right. So give me 1 second to formulate. I think Gauss's law and the definition of flux are in conflict for many of you. I can define flux without talking about electric field. Due to Gauss's law, and when I say that, I mean, I need to be kind of careful. I can define electric flux without ever talking about electric field. Because by definition, electric flux is how much charge I enclose in a box. So I don't ever have to really talk about electric field if I want to talk about electric flux. Gauss's law lets me do that. So if I tell you that I have a box, and this was a real problem one year, and inside of it were 5 charges. And those charges were not known, but the flux was given. You could make a conjecture about how much charge was enclosed because you knew what the flux was. The idea here that flux and charge are separate is not true, because Gauss's law intimately ties them together. So flux is how much charge is enclosed in my box. But I know that that's not, I don't think, the question you're asking. I think the question you're asking is, how is it calculated? Or how do I deal with it? And that part, I think, is harder. Let's consider this for a moment. And to do this, I need to draw this more accurately. So bear with me when I say I want to draw this accurately so you can see it. You should watch more movies. I don't know what Mr. Stonigal's watching today. Anybody know what Mr. Stonigal's watching today? Steinigal? What is it? What's it about? Adam Smith? All right, so let's say for a moment that I have a square, and the square is, this is not drawn great, and I'm not sure this is going to serve the function that I want to do. So I'm trying to answer your question by, my wife just tried to FaceTime me. I'm pretty sure that's a butt dial. We'll give it a second. If she tries again, then we know. But I'm pretty sure it's a butt dial. I don't think this method's going to help, and I'm afraid that I'm just going to lead you more away. So, sorry guys at home. It's not that I'm put on the spot, but I feel like I've already talked about it enough where I need to be careful and maybe talk about it using a different example. Okay, here's what I'm going to do. I got it. I got an idea. And I think this will help. So, Shreyas, imagine a prism. This is one face of the prism. So the prism itself extends into the paper some. So if I was to try and sketch the rest of the prism, I'd be sketching something like, something that looks like that, okay? I'm going to erase those lines in a minute because I can't really draw in 3D particularly well, but assume that this is 10 centimeters wide. So the height of my prism is 10 centimeters. Is that okay? I'll put that over here. So I'm going to erase that because I don't think that will be functionally nice to see with what I'm going to draw next. There's an electric field in this region of space, and I'm going to orient my prism as you can see. So this is the electric field lines as they are in space. And let's assume that this electric field is uniform and passes everywhere, both above and below the prism. Okay? Let's say that the prism has an angle here of 30 degrees and that this face is also 10 centimeters. That makes this face 5 centimeters, and this face, whatever 10 divided by 0.866 is. This would not be 5 centimeters. So you guys take a minute and give me the sides of all three faces real quick, please. All right, so can we get those? Please. But he's wrong. The side I gave is the adjacent side, not the hypotenuse. So if I wanted to find out that top one from just the 30 degrees, I'd have to use tangent. Tangent of 30 would be 5.8 divided by 10. Your calculator is also in degrees, right? And then the other one should have been 10 divided by cosine of 30, which would have given you 11.6. So I think we're right on the money here. Now, let's say the electric field is 1,500 newtons per coulomb. It should not be a difficult calculation for you to recognize that the flux through this prism is 0 because there's no enclosed charge, right? But that doesn't change the fact that there's an electric field here, and I see two sides that are impingent upon the electric field, meaning of this shape, the electric field clearly passes through this face and then passes out of this face. It does not pass through this face and does not pass through the top or the bottom. Everybody follow along with that argument? Well, we should be able to calculate the electric flux through the entire prism. And show that the total electric flux is 0 by doing the calculation for electric flux. This right regular prism has 1, 2, 3, 4, 5 sides. There's the top and bottom. There's the short side and the two longer sides. Everybody follow along? The area of this side will be 10 centimeters times 10 centimeters, or 0.01 meters squared. The area of this side will be 11.6 centimeters times 10 centimeters, or 0.0116 meters squared. I only need those two, but I need them to be able to do the calculation for flux, because I actually will have many fluxes to calculate. There'll be the flux for the top, the flux for the bottom, the flux for the short side, the flux for the 0.01 meter squared side, and the flux for the 0.0116 meter side. Now, it's at this point where I hope we've kind of established that this one's 0, and this one's 0. But this one's clearly not 0. There's clearly electric field passing through that side. We can calculate how much flux there actually is. We know the electric field is 1,500. We know the area of that side is 0.01 meters squared. And we know that the angle between the electric field and the area is 180 degrees. Why? Because the area's got to point away from the center, and the flux is passing into that side. So that's the total flux impingent upon that side. In a similar way, we can calculate the flux on this side. And it's got to be the opposite amount for the total electric flux to be 0. So again, 1,500 times, well, the area this time is going to be 0.0116. But now, got to deal with the cosine here. I've got the electric field in this direction and the area in this direction. What's that area between them? Oh, that angle, I'm sorry, yeah. It should be 30. So times cosine 30 degrees. Now I bet when you add these up, we're going to get 0. In fact, I'm pretty sure of it. But let's do it. 0.01 times 1,500 is going to be negative 15. And the units are newtons per coulomb meter squared. So newtons meter squared per coulomb. What are you going to multiply all that out? It's got to be 15. Because we got this number by dividing by 0.866. And now we're multiplying by the cosine of 30, which is 0.866. So it's got to be 15, positive, newtons meter squared per coulomb. So what's the total flux? 0. Why? There's no enclosed charge. Now, this is not something we ever did when we talked about this in class. But it's all the same skill sets that we talked about in class. When you're looking at a shape that's inside an electric field, you need to ask yourself, what is the electric field relative to that shape? Is it constant along the surface you've drawn? Does it change along the surface you've drawn? Then, what is the shape? Do we have to break it up into pieces, or can we do it as one entire shape? If we break it up into pieces, let's try and arrange it so that many of those pieces have 0 flux. That's what we did here by arranging this. Now, we could have arranged this not like this at all. We could have put it at some weird angle to the electric field, and that would have made the problem harder. Do you think it would have changed the result? No, I don't think so. I think the total electric flux would always be 0. But does that give you an example of calculating electric flux that's different than what we've done so far in class, but still has kind of the similar tones to it? Now, that being said, I don't want to minimize that if you have like an infinite line of charge that has, lambda as its charge density, you shouldn't be grappling with what shape to use here. With an infinite line of charge, I want to pick a shape to get an expression for the electric field that uses the symmetry of my example to my advantage. So I'm thinking immediately, okay, I'm going to go with the tried and true cylinder. Why? Because the cylinder is going to enclose a piece of this line. The cylinder is also going to provide me with 2 parts to my area that are likely to have 0 flux. I can use a cylinder in such a way that I can center it so that if I look down the length of if I look down its length, I can make sure that each part is the same distance away. Why? Because I believe if I'm the same distance away, that's likely how it's going to influence the electric field. So if I wanted to do this particular example again, I would point out, that first, the flux. It's going to be broken up into 3 pieces. One for the top, one for the bottom, and one for the sides of my cylinder. Why? Because I specifically am trying to create the possibility that I have sections of my shape that have 0 flux. That's my exploitation of the symmetry. So top and bottom, 0 flux. Why? Because I think the electric field is going to come out in nice, uniform electric field lines that will be perpendicular to the line of charge itself. It wouldn't make any sense to have set up this line of charge in such a way that it wasn't uniform inside the cylinder. It won't change the result, but it would make this impossible for me to calculate, because I wouldn't have any easy way of knowing how the electric field varied on my surface, nor would I be able to figure out the angle of the electric field going through the top and the bottom. So that's why I try to choose to limit this to a very specific case and try to exploit the symmetry by picking a shape that I know I can utilize to find the total electric flux. When the truth of the matter is, I don't have to do any of that to find the electric flux. The electric flux is going to be based on how much of the charge is actually inside the shape. I mean, right now, I can tell you that the electric flux is going to be lambda times h divided by epsilon naught. That's how much flux there is. Why? Because that's exactly how much charge I've enclosed inside the cylinder. But the actual flux could also be E times pi r squared h. That's also the flux, because this represents the electric field that goes around the outside of my shape, not pi r squared h, 2 pi r h, the area of the outside shell of my shape. Which of these is the flux that they want? It really depends on the question, right? Which variables am I allowed to use in my answer? Now, we tend to use the flux to find the electric field in these problems. But don't get caught up in that. This could be the answer for the amount of flux there is, just as well as this could be the answer for the amount of flux there is. So you can use this perhaps to maybe figure out what lambda is, if that was your question. Or you could use this to come up with an expression for the electric field if that was your question. But when it comes to the flux, either one of these is the answer. So, if it were me, when I was writing an FRQ, this one is probably the one I do. Meaning, I would write it in such a way that you would be misled to think that you had to do this to figure out the electric flux, when you could probably just figure out how much charge was enclosed. And that would give you the electric flux as well. That is the most common thing that they do on the test, is to try and confuse you as to what are you expected to do in the problem. Okay, so does that help Shreyas at all? Yeah. All right. Now, just in closure, we did this a lot. We found electric field from here. But electric field isn't flux, right? And that, separate the words in your mind. Study the idea that they're different. The electric flux is how much electric field passes through an area. And by Gauss's law, it will be equal to how much charge you've enclosed inside that volume. So we could just as easily have one of these questions where you've got a sphere of charge. And I ask, what is the flux? Perhaps what would be the flux inside here? Well, you wouldn't go about finding out how much flux is inside there. You'd go about finding out how much charge is inside here, because that is how much flux there would be. So just understand, if you remember nothing, and go into the test tomorrow, that Gauss's law states that the flux is equal to the charge enclosed. That's what the law is about. We use it to find electric field, but that's not what the law is about. All right. Imagine I have two conducting spheres. But one of them has a imbalance of charge, making it negatively charged as a whole. If I move that close to the other metallic sphere, what could I expect to happen in the other sphere? You should be able to describe that in the other sphere, negative charges will be repelled, revealing positive charges on the front edge, creating an induced charge by creating a charge separation. That this will, in turn, due to Coulombs Law, create a force of attraction between the two. Interestingly enough, I should expect you to be able to extrapolate from here what would happen if I were to connect a grounding line to one side of that sphere. We've not talked much about this, but we mentioned how the ground is a reservoir of charge, and in such a circumstance, we would expect these negative charges to be pushed out of the sphere. Maybe not all of them, but a couple of them. So that if I were to suddenly disconnect the grounding line and take this one away, I would be left with a resulting sphere that now is positively charged. I drove away some of the electrons. Again, just using some of the stuff we talked about in class. The same process could happen if I started with a positively charged sphere and brought it to a neutral sphere. If I did that, what would happen to the charges in the sphere? Can you describe it? Go ahead.
The negative charge would be attracted and the positive charges would be repelled.
Sure. If I went the extra mile and connected a grounding line here, what do you think would happen in this case? Go ahead, Xavier. Well, remember, we can't really move the positive charges, so I think we'd be manipulating electrons. Yeah, we'd probably bring in some electrons from the ground, and this would result in a more negative sphere. This process is the process of charging by manipulating charges in our object. We're using conduction and induction together to charge this sphere by moving its charges. Now, we could also consider what would happen if, say, I had, say, negative 5Q here and positive 1Q here. If I brought these two conductors together, can you figure out what the result would be? What's the total charge now of the system? Matt? Negative 4Q, sure. The system now has negative 4Q. However, we know that that charge will be spread out over both spheres. So if I were to then separate one of these, what would be the charge of both of these spheres? Damien? Yeah. That would be my expectation. These kinds of problems are ones we talked a little bit about. I can imagine, and I think you can imagine, that these would probably show up on the multiple choice section of the test. And we should expect there to be between 5 and 10 multiple choice questions. I think that would be appropriate. This kind of question, I think, is the kind of question you should expect to see there. Any follow-up about this? Still, we're really talking about Coulombs Law and the forces on charged particles. I suspect